Welcome to today's educational video on the topic of air handling units, healthy air quality, achieved efficiently. After a brief introduction to the topic of air quality and energy efficiency, I will explain the two topics with three concrete examples. I will give an overview but will not go into too much detail as there is not enough time. What are the main challenges of ventilation? Opening the windows could be a simple solution after all. That would work if you are near a forest and it is a pleasant 20 degrees on that spring day. However, it can also feel completely different when you open the windows. It is cold, damp or hot, and the desired comfort and especially energy efficiency will suffer. Air quality can also be severely affected, even with less obvious air pollution than shown here in the picture on the right. There may be invisible pollen or fine dust in the air that negatively affects our health. For these reasons, mechanical ventilation systems are required in modern buildings. Their task is to harmonize the aspects of comfort, air quality, and energy efficiency. Comfort and energy efficiency are undoubtedly interrelated and influence each other. In my opinion, all three aspects are very important. What does mechanical ventilation look like? What does it involve? The heart of mechanical ventilation is the air handling unit. Depending on the building situation, this device is located on the roof, in a plant room, and is designed as a decentralized or centralized solution. Regardless of where the air handling unit is located, its task is to draw in outdoor air, filter it, clean it, and condition the air in terms of humidity and temperature. The air is then brought into the building, guided to the zones and rooms via air ducts and blown in accordingly. On the other hand, polluted air is extracted via exhaust air ducts and led outside via the air handling unit. In the process, the energy that is in this air is recovered. In this educational video, I mainly focus on the air handling unit in combination with air quality and energy efficiency. Before I get to the concrete examples, I would like to introduce the two aspects. A separate educational video has already been held on the topic of healthy indoor air. I would like to summarize the most important points again here. At the center of the 7 basics for healthy indoor air are precise and continuous measurement and monitoring of indoor air quality. You can only control and optimize what you know. The second basis is a precise air supply to the zone and a controlled removal of polluted air. Furthermore, a sensibly designed air dilution and airflow profiles are important. In addition to healthy indoor air quality, these contribute greatly to increased comfort. The fourth basis is active pressurization of the building envelope and rooms. An example of this is a special operating room in which gauge pressure prevails. This ensures that the interior of the room does not come into contact with contaminated outdoor air. The three other fundamentals all relate to the air handling unit. On the one hand, correct control of temperature and humidity is central, and a fortnight ago we learned that 40 to 60% relative humidity is ideal for our health. Effective filtration is self-evident, and the last of the 7 basics guarantees an adequate amount of outdoor air, so as to be able to guarantee a balanced room balance. Healthy indoor air quality is certainly the focus, but we must not lose sight of the energy required to achieve it. Achieving energy efficiency is not only relevant because of global warming, but also because of rising costs. The building sector is said to consume a huge amount of energy. Here are some facts. 35% of global energy consumption is attributed to the building sector. 40% of building sector energy is used within buildings for heating, ventilation, and air conditioning plants. You can now imagine the great optimization potential behind this. About 2% of new, energy-efficient buildings are built per year. This figure has prompted the European Commission to launch a renovation wave initiative with the aim of increasing the renovation rate. This initiative is also known as the European Green Deal. There are other initiatives such as the Energy Performance of Buildings Directive or the Eco-Design Directive, to name but a few. In addition to these political initiatives existing at the level of the European Commission, there are also various smaller measures that should also be taken into account and are very important. My following examples are aimed precisely at these measures. Where are my 3 specific examples located? Let's look at our air handling unit. The first thing to mention is effective filtration in the supply air or extract air. The second topic concerns optimized fan control to ensure that an adequate amount of outdoor air is supplied to the system. This should also be understood in the context of VAV zone regulation. My third point is aimed at the correct control of temperature and humidity with pressure-independent valves. I will start with effective filtration and filter monitoring. We spend approximately 90% of our lives indoors in buildings. Therefore, good indoor air quality is essential for our health. This can be achieved with effective filtration. What kind of impurities are there? The following table shows types of contaminants and lists the contaminants according to the corresponding particle size in micrometers. For example, biological contaminants include viruses, pollen, or even fungal spores. Different types of dust such as coarse dust or fine dust are also listed in the table. Particulate pollutants include soot, but also tobacco smoke. For the sake of completeness, gas molecules are also listed in this image. But I will not go into these in this educational video. The image also shows which filter types and filter classes can be used to filter out the corresponding impurities. In the yellow area between 0.01 and 1 micrometer are the filters for suspended matter. In the green area, which partly overlaps with the yellow area, you can filter out the corresponding particles with fine dust filters. And last but not least, there are the coarse dust filters, which eliminate the largest particles. With all these types of filters, you can filter out a relatively large amount from the air and thus do a lot for our health. However, we must now be aware that this filtration in an air handling unit means additional energy expenditure. A higher energy input inevitably means higher costs. In this transparent view of an air handling unit, you can see the various components and the volumetric flow that passes through them. Each of these components causes a pressure drop and thus also a higher energy requirement of the ventilator in order to be able to maintain the nominal volume flow. I found a very good example from the company Unifil. It is about the life cycle costs of a pocket filter. The image shows impressively that 75% of the life cycle costs are for energy. It is therefore very worthwhile to take this aspect into account. In order to optimize these energy costs, high-quality filters are the obvious choice, complemented by perfect filter monitoring. If a filter is present, the eco-design regulation for ventilation units requires monitoring of the contamination. This can be done in 2 ways, either with a visual display or with an acoustic warning device in the control unit. So what does a possible example look like in practice? For an optical display, differential pressure gauges are used. On these, the differential pressure across the filter can be seen visually in Pascal. There is also a manually adjustable pointer that indicates the threshold value. If this value is exceeded, the filter must be replaced. With the acoustic warning device, the differential pressure above the filter is also measured. A differential pressure switch is used for this. This switches as soon as the preset threshold value is exceeded. However, this threshold value is also set manually here. The switch setting is continuously monitored by the control unit, which can then indicate acoustically when a filter change is necessary. But how do you know which threshold value to set? How do we arrive at this value? I would like to answer this question in this slide. The filter monitoring is shown schematically on the bottom left. The ventilator with the corresponding air volume flow and the differential pressure switch above the filter are visible. The warning device is also shown here symbolically. The first thing to know is that the differential pressure threshold value refers to the nominal volume flow. If the filter is new, there is an initial pressure at the nominal volume flow. As the filter becomes increasingly dirty, the final pressure is reached at which the filter must be replaced at the latest. But where do these values come from? The initial pressure is listed in the filter manufacturer's data sheets. There, the initial pressure is given for the corresponding nominal volume flow. The final pressure can now be calculated on the basis of the VDI 3801:1 standard. For coarse dust filters, this value is calculated from the initial pressure plus 50 Pascal, or the threshold value is set at 3 times the initial pressure. The smaller value of the two just calculated applies. For a fine dust filter, 100 Pascals are used instead of the 50 Pascals. This information can also be found in the documentation of the air handling unit manufacturer, who lists the values for a fine dust filter, for example. For the sake of completeness, I have listed the hygiene guideline VDI 6022. This requires a filter change over time. However, I will not go into detail about this guideline here. What is the problem with regard to energy efficiency in this constellation? To do this, you have to look at the whole thing in the partial load case. More and more devices in new buildings are demand controlled. In many cases, this means that the nominal volume flow is rarely or never reached. The system therefore runs at partial load, often in the range between 20% and 80% of the nominal volume flow. We now calculate the initial and final pressure for this partial load case, shown in the image with the black and red curves, respectively. For this we need the general filter characteristic curve, which can be calculated with the following formula. It is the product of a constant C, which depends on the filter type and the contamination, and the root of the differential pressure. If you change this formula accordingly, you can calculate every single point on the red curve. Provided you know the nominal volume flow, the final pressure at nominal volume flow, and the current volumetric flow. This allows you to calculate the corresponding final pressure. The following schematic diagram shows that one can measure the required values with a differential pressure sensor above the ventilator or above the filter and thus know the threshold value for the current partial load operation at any time. With the measured differential pressure above the ventilator and the manufacturer's K value, one can calculate the current volumetric flow. Hence our recommendation to use differential pressure sensors instead of differential pressure switches. This is the only way to know the current differential pressure, which is necessary for calculating the final pressure in part load operation. In this way, you can detect a filter that is too dirty much earlier and thus effectively save costs. I will show you how much this can be with the following two calculated examples. Let us now consider two cases A and B for a medium-sized air handling system with today's constantly rising energy prices. In case A, we assume that within 2 years a fine dust filter will be completely soiled and the final pressure will be reached. In case B, however, we replace the filter after only 1 year. The energy saved in this way amounts to 670 kilowatt-hours and €230 in saved costs. That is a considerable amount. However, we must now also correctly include the costs for the filter. This reduces the amount saved somewhat. In this example, I want to show that a timely filter replacement saves energy and thus considerably reduces the operating costs. Now I come to the second example, in which I discuss the appropriate amount of outdoor air and the optimized fan control. Optimized fan control is based on a foundation that must first be known. This involves room control with VAV, which ensures an appropriate airflow rate for every situation. In order to save even more energy, you can implement optimized fan control, which we at Belimo call fan optimizer. This ensures efficient control of the air handling system. I'll start with the room control by the VAV devices. The picture shows a building with 2 different rooms occupied by a different number of people. The picture also shows the air duct network with the supply air duct, the extract air duct and the air handling unit with the ventilators. As I mentioned at the beginning, it is essential to measure the air quality. Here you do this with a room probe that measures the CO2 concentration in the room. The CO2 value correlates very well with the number of people in the room. The correct airflow rate must now be supplied according to the demand. This is ensured by VAV units in the supply air and extract air, and thus a balanced room is obtained. The image on the right shows nicely that there is a linear relationship between the demand and the corresponding volumetric flow. If there is 100% demand, the VAV units supply the maximum volumetric flow Vmax. If there is no demand, a minimum volumetric flow Vmin is still guaranteed. What we also need to know is that the VAV system is a pressure-independent system. Despite pressure fluctuations in the channel, the system ensures the desired air volume flow at all times. The points just mentioned are the basis for the optimized fan control, which gives us the exciting opportunity to save energy. So how does this optimized fan control work? Let's look at an example where all 3 rooms of a building are fully occupied. The picture shows the VAV controllers in the supply air. The VAV controllers in the extract air have been omitted for a better overview of the image. They show the same behavior as the VAV controllers in the supply air. An individual room control is shown, which controls the air volume flow as required. The majority of the damper position is open for all rooms, and thus a maximum volumetric flow is guaranteed to flow into the room. Outside the rooms, the control of the air handling unit is shown with the ventilator. The state of the art today is that in most cases you control the duct pressure and want to keep it constant. For this purpose, the pressure in the channel is measured and the ventilator is controlled accordingly. This set point is determined for nominal load operation. A correct pressure loss calculation is necessary to determine the correct reference value. This is the only way to guarantee that the last VAV controller is supplied with sufficient air volume flow in nominal load operation. It is important to mention in this example that these 2 control loops act independently of each other and thus the energy efficiency is not optimal. Why is the energy efficiency not optimal? Let's look at the partial load case. The rooms are now occupied differently. Only one room is occupied by one person. The other rooms are unoccupied. This means that the VAV controllers for these unoccupied rooms are almost closed, because these rooms only have to be supplied with the minimum air volume flow. It is precisely this behavior that is the cause of the energy loss, since the duct pressure still corresponds to the pressure for nominal load operation, but the VAV units of the unoccupied rooms must destroy pressure. Pressure destruction, however, always means energy that we have to expend for this purpose. And this energy expenditure generates unnecessary costs. In addition to the cost situation to be considered, pressure destruction also means possible higher noise emissions in the rooms. How do you do this better? To improve this situation, the optimized fan control now comes into play. Let's assume the same partial load case again. The rooms are therefore occupied differently again. The majority of the VAV controllers are closed. What is now different from the previous example, however, is an additional link between the individual room control, which now contains the fan optimizer function, and the ventilator control. What does this control do? It analyzes the damper position of each individual VAV controller and recognizes in our example that the majority of the damper position is closed. The control with integrated fan optimizer function now controls the fan, which reduces its speed. This causes the VAV controller to open the damper position. However, exactly the same amount of air is still supplied to the individual rooms, because our VAV volume control equipment is a pressure-independent system. We can therefore save energy by reducing the speed of the ventilator. Now I will explain this in a little more detail. We will look at the system and fan characteristic curve. The upper diagram shows the volumetric flow on the x-axis and the differential pressure across the ventilator on the y-axis. The individual speed curves of the ventilator as well as the system characteristic curve can be seen. The lower diagram also shows the power consumption of the ventilator, which increases towards the bottom. The system runs at nominal load at the design point, shown here in red. Without optimized ventilator control, the differential pressure over the ventilator is kept constant even with a reduced volumetric flow. We are talking here about constant duct pressure control. The red dot moves horizontally to the left. An expected reduction in performance, as shown in the lower diagram with the blue arrow, also occurs. Now let's look at the diagrams in the case of fan control with the fan optimizer function. In this case, the operating point moves along the system characteristic curve, as no constant duct pressure has to be maintained. The power reduction of the ventilator is also higher and it is therefore much more energy efficient. My explanations are very theoretical. However, we have also tested this in practice. We did this in cooperation with the Lucerne University of Applied Sciences and Arts. It is an older study, but it remains valid today. To do this, we converted two identical sectors at Belimo's headquarters in Hinwil. Sector B we operated with conventional duct pressure control. In Sector C we used the optimized fan optimizer control. Both zones have their own air handling unit and their own VAV zone controllers. The power of the ventilator was recorded over several months. You can see very nicely that with a fan optimizer function 20 to 60% energy could be saved. That is enormous. You can also see that when the system runs in partial load mode with lower volumetric flows, the savings increase disproportionately. The fan optimizer function thus provides the basis for energy-efficient operation of the system. Now I come to my last example, which is about the correct control of temperature and humidity. This relates to the valve for the air cooler and air heating coil. Where are valves used? Wherever air-water coils are used in an air handling unit. This can be in a preheater, in heat recovery in runaround coil systems, or in the area of the air heating coil. These valves are also used in the air cooler or in active dehumidification with the necessary reheater. The following slide shows once again the typical hydronic circuits for air handling unit with the corresponding heating coils. My colleagues have already held educational videos on these circuits. Therefore, I will only explain them very briefly. For the air heating coil, we recommend an injection circuit with a two-way valve or the mixing circuit. The decision for one or the other circuit depends on whether it is a pressurized system or an unpressurized system. In the case of an air cooler, we recommend the throttling circuit. Of course, other constellations are also possible. It should also be noted that controlled dehumidification is not possible with an air cooler. In the case of an air heating coil with throttling circuit, there could be a risk of frost or correspondingly increased temperature stratification. What is the goal that you want to achieve with these heating coils? You want to achieve a constant supply air temperature. Since water is incompressible, pressure fluctuations can occur in the system. The switching on or off of consumers or different load requirements can also lead to such pressure fluctuations. As a rule, however, such influences are corrected with the control and the desired constant temperature is obtained. In extreme cases, for example with older systems or if the system has been further expanded, the temperature of the supply air may also begin to fluctuate. Pressure-independent valves counteract this effect and eliminate these fluctuations. What types of pressure-independent valves are there? There are the mechanical and the electronic pressure-independent valves. However, I will not go into detail here. Only this much: both systems have their advantages and disadvantages. With the electronic pressure-independent valve, there is full system transparency because you measure and know the flow rating and can use this for further evaluations. Where are the clear advantages of a pressure-independent valve? The left side shows a system with pressure-dependent valves. The hydronic balancing for such a system is very complex and time-consuming, and this time costs money. In addition, a balancing valve is needed for each consumer, which also costs extra. These systems are designed for full load operation. But what about partial load operation? Does the system still run as well then? Therefore, systems with pressure-independent valves are clearly at an advantage, because with these the hydronic balancing is carried out automatically and permanently. Another advantage of using pressure-independent valves is that, analogous to the fan optimizer, the pump optimizer function can now be used here. This analyzes the valve position of each individual consumer. If the majority of these valves are closed, the pump optimizer function reduces the speed of the pump with corresponding energy savings. This is also an energy-optimized solution. The last slide on this topic shows another way to save energy. As I said, you can optimize what you know. If you know the flow rating and the return temperature of an electronic pressure-independent valve, you can calculate the power at the consumer. The following image shows such values recorded in practice. The red dots symbolize the power. The light blue dots show the delta T. It is easy to see that above a certain flow rate, the power output begins to stagnate. We speak here of a saturation of the system. It is highly recommended to operate the system in a range where there is no saturation. This can save a considerable amount of energy. System transparency is therefore important and the prerequisite for operating the system in the optimal range. Now I come to my summary and the most important points you should take away from this educational video. Regarding effective filtration, we recommend the use of differential pressure sensors. This is the only way to know the differential pressure across the filter. If you now also know the current volumetric flow, you can also determine the correct final pressure in the partial load case and thus replace the filter in time to save energy and costs. With the appropriate amount of outdoor air, a VAV zone regulation is recommended. This ensures the supply of fresh outdoor air as required in any situation. It is a pressure-independent system that provides the basis for saving energy. With the optimized fan control by the fan optimizer, the damper positions are taken into account and thus unnecessary pressure drop is prevented. Now to the last point on my slide. Remember that pressure-independent valves are the basis for controlling temperature and humidity correctly. If you know not only the flow rating but also the output power, saturation of the system can be prevented and energy consumption optimized. Before I come to the end of my educational video, I would like to give you the following advice. We have set up an additional page for air handling unit on our website. Our solution book on air handling unit can also be found on this page. The aim of this solution book is to build and expand knowledge and create a better understanding of ventilation and air conditioning solutions. You can see the topics as well as the target audience here on my slide. So, now I'm at the end of my presentation. I hope you enjoyed it and found my information useful and interesting. Thank you very much.